All right, so we have the notes for section 5.1, which deals with the extreme values of functions. So our objectives: determine the local or global extreme values, and determine the applicability of the extreme value theorem. So we've got a couple of definitions. The absolute or global extreme values. So it says here, let f be a function with domain D, then f of c is the absolute maximum value on the domain, if and only if every value of the function is less than or equal to that specific value. So remember, f of x and f of c, these are y values. So this is saying that f of c is the largest y value because all other ones are less than it. So that's a maximum. You have a minimum if all other y values are always greater than or equal to your specific y value. So it's the lowest possible y value. So absolute or global maximum minimums are called absolute extrema. Extrema is just the generic term for a maximum or minimum. We often omit the term absolute or global and just say maximum or minimum. So the maximum value of the function, minimum value of the function. Okay, so here it says find the extreme values of f of x equals the cosine of x and g of x equals sine of x on the interval negative pi over 2 to positive pi over 2. So for cosine x, negative pi over 2 is actually over here, positive is here. So the cosine function looks something like this on that interval. So that's actually at 1. So the maximum value is equal to 1. That's the largest value it takes. The minimum value is equal to 0, the smallest value it takes on that interval. For sine, between negative pi over 2 and positive pi over 2, the graph looks something like this, where that's 1 and that's negative 1. So for this one, the maximum is equal to 1, the largest it gets. The minimum is equal to negative 1, the smallest that it gets. So you can do this just by looking at the graph if you have a closed interval. All right, the extreme value theorem down here. If f of x is continuous on some closed interval like we had up here, then it is guaranteed to have both a maximum and a minimum. Now, some functions may not have one. For example, if I take the graph of x squared, looks like this. This function only has a minimum because this graph goes up forever. But this also has an open interval. It's allowed to go forever left and forever right. If I close it, if I say only between negative 1 and positive 1, that drops endpoints on my function. And now I do have maximum values because it never goes above that as long as it stays between negative 1 and positive 1. So if you close an interval, you're guaranteed a maximum and a minimum. Oops, too many pages. Okay, so we got local or relative extreme values. So local maximum mins are in a given region, the largest or smallest values, not necessarily the overall largest or smallest. So these are referred to as relative extrema because they're not for the whole function, they're just in their specific area. Absolute extremas also are local because if they're the most maximum, they're the biggest point in the area. Like, so for example, if I have like this function here, so these 2 points are local maximums, that's a local minimum. Now this function does not have an absolute minimum because the graph goes down forever. But this point here is also an absolute maximum because it's the largest maximum value. So local max, also absolute max. Local minimum, and this function has no absolute minimum because it goes down forever. So there is no bottom to the graph. So to find extreme values occur where the derivative is equal to 0. Because if you think about the tangent lines on this curve, when you hit the peak, the tangent line becomes horizontal for a split second because the slope becomes 0. So that's why you can use this to check. Critical points occur where the derivative is 0 or where it doesn't exist. So meaning you have a vertical tangent, something like that. Stationary points at which f prime of 0 is called the stationary point. Now, just because your derivative goes to 0 doesn't actually mean you necessarily have a local maximum or a minimum because your graph could do something like this. It could go up, then flatten, and then keep going up. It's like right here, the derivative is 0. It's flat, but it's not a max or a min. So it's just a stationary point. So you do have to check. This gives you a list of possible absolute maxes or mins, but you do have to check and look at the graph to necessarily see. Okay, so it says find the absolute maximum minimum values of f of x equals x to the 2/3 on the interval -2 to +3. So I need to find my critical points first. So I need f prime of x. So that's the derivative. So exponent comes out front, count down the exponent by 1, and critical values occur where the derivative is equal to 0. So I need to solve this equation, or where it's undefined. So divide both sides by 2/3 gives me this, because 0 divided by 2/3 is still 0. Now this is actually 1 over x to the 1/3, because it has a negative exponent. If I try to solve this, if I do cross products, I'm going to get, so that over 0, so multiplying the diagonals, I get 0 equals 1, which is a false statement, which means this has no solutions. The other way to think about it is x cannot be 0. So that number there is actually a critical value, a value that is not allowed, because it gives me an undefined tangent if x is 0. So what happens is I have 3 numbers to check. I need to figure out what f of -2 is, f of 0, and f of 3, and see what my graph looks like there. So when x is 2, or sorry, when x is -2, I get the, I'll just turn my calculator, -2 raised to the 2/3. This gives me a value of 1.59. f of 0 is 0, because 0 to any power is 0. And f of 3 to the 2/3 is about 2.08. If I look at the graph, let's see here, x to the 2/3, draw. So there's my graph. Actually, let's reset my view window. There we go. So it draws that lovely little birdie shape. So does something like that. So 0 here is a minimum, and it's the absolute minimum, because it's the lowest value here. At f of 3 and f of 2, so f of 3 here is the absolute maximum, because it is the largest the graph goes. This piece left of, so if that's -2, this over here is +3. The graph doesn't exist, as far as I'm concerned, outside of -2 and 3. So -2 will be a maximum, but it's not the absolute maximum, because this value is higher up. Okay, so just some more examples of this. Just this page, it looks like. So find the extreme values of 1 over the square root of 4 minus x squared. So I'm going to rewrite this first. This is 4 minus x squared raised to the -½ power. It's a ½ power because it's a square root. It's negative because it was on the bottom of the fraction. So I need to find the critical values. So I need to find f prime first. So this is a chain rule problem. So exponent multiplies out front. Leave the inside alone. Count the exponent down by 1. And then multiply by the derivative of the inside. So times -2x. So I can multiply the -½ and the -2. So this is actually just x quantity 4 minus x squared raised to the -3/2. So I'm going to set this equal to 0. Now, just like before, negative exponents actually sit on the bottom of fractions. So I do this. Now, to find the critical values, I need the numerator to be 0, because that'll make the function actually equal to 0. But I also need the denominator equal to 0, because that gives me the undefines. So x equals 0. So that's one critical point. That's the numerator equal to 0. And then I also set the denominator equal to 0 and solve as well. So to get rid of the 3/2, I would just raise both sides to the 2/3 power, but 0 to the 2/3 is still 0. So the exponent essentially disappears. So this becomes 4 equals x squared. So when I take the square root, I actually get 2 solutions, positive or -2. So I have critical values at 0, 2, and -2. So I need to find f of 0, f of -2, and f of, +2. Now notice these numbers are going back into my original equation. They're not going into the derivative, sorry. These two here, a -2 and +2, they're not going to work. Because if I plug -2 in, I get 4 minus 4 on the bottom, which is 0. Square root of 0 is 0, and I can't divide by that, so there's actually no solution here. These graph functions are undefined. F of 0 is going to be 1 over the square root of 4, which gives me 1/2. If I look at the graph of this guy, 1 over the quantity, the square root of the quantity, 4 minus x squared, close parenthesis, it gives me that little shape. So what I have here, so down here, I have a minimum. So this value is a minimum. These values are technically maximums. But you have to be careful with, you'd have to do a limit step essentially in order to find them. Okay, let's see here. Find the extreme values of this function. All right, so we've got a piecewise here that switches at 1. So left of 1, so for f prime for the top, so this is when x is less than or equal to 1, our derivative is -4x. And when x is more than 1, our derivative is 1. So this will never equal 0, so there's no critical values here. If I set -4x equal to 0, I get x equals 0. So if I look at the graph, so x equals 1 is where my graph function switches. So 1, 2, 3. So you have, that'd be an open circle. And then it goes, so that's this part. Let's see here. When x is 1, this function would fill that in. And then when x is 0, I would have 4, 5. So this thing is actually parabola, looks like this. So here you have a minimum, because that's the lowest point. And up here you have a maximum. So the maximum is actually at the point 0, 5. The minimum here is at the point 1, 3, where the two functions meet. Okay, and the last one, find the extreme values of the natural log of the absolute value of x over 1 plus x squared. Okay, so let's see how to do this guy. So f prime, the derivative, so derivative of the natural log is 1 over whatever's inside the natural log times the derivative of what's inside the natural log, which happens to be a quotient rule. So that's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So this becomes x squared plus 1 over x, because to divide something by a fraction, you just flip it. And over here, you have 1 plus x squared minus 2x squared all over 1 plus x squared squared. So this is x squared plus 1 over x times 1 minus x squared over 1 plus x squared squared. Okay, so this term here, x squared plus 1 and 1 plus x squared are actually the same term, so that guy can cancel one of those out. So I'm left with 1 minus x squared over x times 1 plus x squared. So I need to find my critical values. So to do that, I need to set my numerator equal to 0 and set my denominator equal to 0. So this would become 1 equals x squared, so x is plus or minus 1 when I take the square root. This one gives me x equals 0. I also then have to split to do that. So this will give me x squared equals -1, which has no solutions. So my critical values are at 0, -1, and +1. So f of 0, f of -1, f of +1. So if I plug 0 in, I have the natural log of 0, which is actually undefined, as you can't do that. So this actually has no solution. There is no value there. F of -1 would be, let's do some math here, -1 on top. On the bottom I would have 2, but absolute value, so this would just be the natural log of 1/2. And when f is 1, I'm going to get 1, same thing, the natural log of 1/2, which, if you want the decimal, ln 0.5 is about -0.69. And if I look at the graph, let's see here. Oops. The natural log of the absolute value of x over quantity 1 plus x squared, close, close, draw. So the function looks like kind of like a weird funny bird. So it does something actually like that. So here, there, that's my, that's at 1, at -1. So these points are both maximums. They also happen to be the absolute maximums. And down here, the function is undefined, so there is not actually a minimum there. So just because you have a critical point does not mean you actually have a max or min at that location. Which brings us to the end of the section.